Welcome to today's Explainer. We're jumping right into a fascinating journey, starting with some foundational algebra, but quickly working our way toward a really specific and honestly super powerful goal: mastering the logical steps of reversing mathematical processes. If you've ever found yourself wondering how to systematically undo a complex calculation just to figure out where it all started, well, you are absolutely in the right place. Okay, let's dive into this with a question that's going to frame our entire discussion. If a mathematical formula naturally moves us forward from a starting point to a final answer, how do we put it in reverse? In this explainer, we're going to unlock the actual mechanics behind inverse functions. We're talking about the exact logical steps required to take a finished product, completely deconstruct it, and trace it all the way back to its raw ingredients.
So here's our roadmap. First, we'll meet the function machine. Second, boundaries and combinations. Third, the logic of inverses. And finally, functions in the real world. Let's get started.
Section 1. Meet the function machine building the forward engine.
At its core, a function is simply a rule. Actually, I want you to think of it exactly like a physical machine on an assembly line. You have an input, right? That's the raw material you literally drop into the top of the machine. The machine then applies its specific internal rule. So maybe its rule is to multiply your number by 2 and then add 1. Finally, it produces exactly one unique output. You drop in a 5, out pops an 11. It's a predictable, mechanical, and highly reliable process. Now, how do we actually translate that physical machine concept into written mathematical language? In early algebra, you're probably used to seeing equations written as y equals 2x plus 3. But as the math gets more advanced, we shift to function notation. F of x equals 2x plus 3. And I have to emphasize this heavily because, well, it trips up so many people. F parenthesis x does not mean f multiplied by x. The f is just the name tag for the machine, and the x inside those parentheses is simply the input you're dropping into it. But there is a golden rule here. For a mathematical relation to officially be classified as a function, every single input can only go to exactly one output. Notice how a valid function behaves. Input 1 goes to output A. Input 2 goes to output B. Perfect. It's predictable. Now imagine a broken machine, where input 2 goes to A, but also to B. Imagine pressing a button on a vending machine and it gives you a soda one day and a random shoe the next. That machine is completely broken. It is not a function.
Moving on to Section 2, boundaries and combinations, fuel rules, and linked machines.
So every machine has boundaries, and in functions we call these the domain and the range. The domain is the set of all possible input values. Basically, it's the specific type of fuel our machine is allowed to accept. The range is the set of all possible output values that the machine can actually produce. For example, if your machine's rule is to square a number, your range will always be 0 or positive. I mean, a squared real number is never negative, right? So that boundary is strictly forced by the machine's rule itself. Let's see how this builds when we introduce mathematical constraints. You can't just feed any random fuel into any machine. You'll cause a mathematical disaster. If your machine involves a square root, your domain constraint is that you cannot use negative numbers, keeping your valid domain from 0 to infinity. If your machine involves fractions, like 1 over x, you absolutely cannot divide by 0. That literally breaks reality. So your domain just has to skip right over 0. You always have to check your fuel before starting the engine. But what happens when one machine just isn't enough to get the job done? Well, that's where we use composite functions. This is where we link two completely different machines together on the assembly line. The notation f of g of x simply means you take your raw input, x, and drop it into machine g first. Whatever output machine g produces instantly becomes the new input, the immediate fuel that you drop into machine f. You're essentially nesting the processes together. Which brings us to Section 3, the logic of inverses running the machine backward. So the crucial point here is, how do we untangle all these gears? If a function moves us systematically from an input to an output, an inverse function is the ultimate undo button. It runs the entire machine in reverse. Consider the logic behind it. If function f turns an input of 5 into an output of 13, then the inverse function, which is written as an f with a little -1, takes that 13 and mathematically turns it right back into a 5. It perfectly retrieves that original input.
I want to drastically slow down here for a second and walk through the specific 3-step logical algorithm used to build these reverse machines. This is the core logical step behind inverses. Let's say we want to find the inverse of f of x equals 2x plus 3. Step 1, replace f of x with y just to make the algebra a bit cleaner, giving us y equals 2x plus 3. Step 2, and this is the logical core of the whole concept, swap x and y. Because inverses, by their very definition, swap inputs and outputs, we literally flip reality by swapping the variables in the equation. So now we have x equals 2y plus 3. Step 3, solve for your new y. We subtract 3 from both sides, getting x minus 3 equals 2y. Then we divide by 2. We end up with y equals x minus 3 all divided by 2. And boom, that new equation is your inverse function. You just logically untangled the rule and successfully built a machine that runs entirely backward. But beware, guys, there are some serious traps when reversing these machines. Let's rapid fire through the most common mistakes people make. First, again, treating f of x as multiplication. Second, forgetting those domain fuel restrictions we just talked about. Third, ignoring brackets while substituting values, which totally ruins your order of operations. Fourth, and this is a massive mathematical trap, confusing inverse functions with reciprocals. F inverse of x does not mean 1 divided by f of x, it means the reverse logical process. And finally, applying composite functions in the wrong order. Remember, running machine g then f gives a vastly different result than running f then g.
All right, section 4, functions in the real world, and why this matters.
Why do we actually need to build and reverse these mathematical machines? Well, because they literally run everything around us. Distance traveled over time, daily temperature fluctuations, mobile data usage, population growth, business profit, currency exchange, electricity consumption. Every single one of these is modeled by a function. And when an analyst needs to work backwards, say they know the final electricity consumption of a city and need to find out exactly what time of day triggered the spike, they rely entirely on the logic of inverse functions to trace that output right back to the input.
Sometimes, though, the real world is messy, and one single rule just isn't enough. And this is where piecewise functions come in. A piecewise function is a highly adaptable machine that actually changes its own internal rules depending on the situation. Think about a tiered mobile data plan, right? If your data usage is under 5 gigabytes, you pay a flat rate. That's one rule. But if your input goes over 5 gigabytes, the machine instantly switches to a completely different rule, charging you per extra megabyte. It's like a smart machine. From calculating global currency exchange to modeling the population growth of our cities, functions truly do run the world. We've seen how to build them, how to feed them the right domain fuel, how to link them together, and most importantly, the precise logical steps required to untangle their gears and reverse them. We've conquered the inverse machine. But I'll leave you with this final thought. The next time you see a complex system in the real world producing an output, whether it's the stock market or your own social media feed, do you now have the logical tools to reverse engineer it? Thanks for learning with me on this explainer. Keep asking great questions and keep figuring out how the mathematical machines around you really work.